Hello everyone, this is the lecture for section 5.2, unit circle, sine and cosine functions. So, in section 5.1, we covered angles, right? And basically just got comfortable with them and started to work with degree angles, right? From 0 to 360 degrees. And we worked with radian angles from 0 to 2 pi radians all the way around, right? Okay. In this section, we're going to cover essentially the basics, the absolute basis, the foundation for trigonometry, and that is the sine and the cosine function. Okay, so the first thing that I need to cover is this right here. Okay, first of all, right, note this, that this is supposed to be a right triangle. So a right triangle is supposed to be a triangle that has one right angle. And we denote it by a box, something like that. There it is. Okay, so for a right triangle with legs A and B and a hypotenuse C, okay, we have this result right here. A squared plus B squared is equal to C squared. You guys should remember this from geometry in particular, right? This is Pythagorean theorem. Okay, and I'm gonna skip doing the example. I want to do it actually during class. Okay, so if you want to try it, go ahead. Okay, but I'm gonna skip. I'm gonna have everybody do it in class with everybody else. Okay, but now what I want to do, right? I want to go ahead and start to define the sine and cosine that we're gonna do. Okay, so everything in geometry and, well, not geometry, sorry, trigonometry is based on these two functions, sine and cosine. Okay, so that's what I'm going to do right now. I'm going to define sine and cosine. Okay, to visualize a little bit of our work, we'll be using what's called the unit circle. Okay, the unit circle is basically any circle of radius 1. Okay, so what I'm saying is this. See this r that's right here? That is my 1. My radius is of 1. Okay, so now suppose I go an angle around. Okay, and I go that angle is some measurement t. Okay, then the cosine of that angle t is defined to be the horizontal distance to get to this point on the unit circle. Got it? Sine of t is defined as the vertical distance to get there, to that point, that same point. Okay, so that gives us automatically, it gives us this definition right here, that the cosine is basically your x measurement and the sine is basically your y measurement, or you can remember it this way as the ordered pair. So if you want to get to a point xy, if you want to get to this point right here, right, it's got an x and a y value, right? The other way you can do it is you can go around a circle of radius 1, right? You can go around a circle of radius 1 by an angle t, whatever that angle is, right? And it'll hit the same spot, right? The cosine of t is going to be that x measurement, and the y measurement is going to be sine of t. Okay? All right. That's a nice basis. Okay? Now, we usually don't work with circles of radius 1. We use circles of lots of different radii. Okay? Excuse me. So what we're going to transition to now is using a circle of radius r. So instead of having a circle of radius 1, I'm going to call this now circle of radius r. Okay? Okay. And I want to still get to this point right here, this xy point that's right here that I made a little bigger. Okay? And again, suppose that I'm going to subtend a little bit of this circle by an angle T. So I'm going to go by this angle right here. Okay. There are three other names that we can give this triangle in particular. So you guys see that there's this triangle right here. 1, 2, 3, right? You see that triangle, okay? There are three other names for the portions that I'm going to be referring to, okay? So for this angle T, the side that is directly next to it, we call that the adjacent side, okay? For this side opposite, right, we call that the opposite side. Go figure, right? And then for this radius right here, right, we're going to call that the hypotenuse. Okay? Okay. So notice what we have here, right? We have three more names, right? That radius is now some rando length now, right? We don't know. We don't know the length, okay? But we can go ahead and define the x and y variable that's there. We can define this point based off of these three lengths, 1, 2, 3, okay? And that is where we get this phrase, so katoa. Okay? So, here we go. We say that sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is equal to opposite over adjacent. Okay? Those are the things that are down here at the very bottom. Right there. Okay? This is how people tend to remember sine, cosine, and the very last one there, tangent. Whenever we talk about trig stuff. Okay? So now I have these definitions at the tail end, right? That, that, and that. So if we take a look at what we have here, and I'm going to go ahead and use my, actually I'm going to use red. There we go. Okay. So if we take a look at this triangle that we have here, right? The adjacent side, that is going to be equivalent to saying the x, right? Because that's what is here, right? And then the opposite side, that's going to be equal to the y, right? Because that's what we have here. So then the other way that we can define these is as these that are at the tail, the things that are highlighted in blue now, right? That sine is equivalent to y over r, right? It just so happens to carry the same opposite over hypotenuse, right? Cosine is adjacent over hypotenuse, so the x over r. And then the opposite is, the tangent is opposite over adjacent. So y divided by x. Okay? And there you have it. That is sine, cosine, and tangent. Okay? Okay. This is the actual, these right here, the things that are in blue, are the actual definitions of sine, cosine, and tangent. They are essentially, let me scroll a little further down, they are essentially the ratio of the hypotenuse and how far vertically or horizontally you need to go to get to this point right here. They're a fraction, right, of either the horizontal or the vertical component compared to your hypotenuse of your triangle. Okay, that sounds super complicated. The best explanation that I can give you, or something that people tend to remember is if you guys remember what an Etch-a-Sketch is, okay? The Etch-a-Sketch is let me scroll over this way a little bit. I'm just gonna draw it right here. Hopefully you guys remember this toy. It was a toy. It had two knobs, right, and then a big, huge, massive screen. Ugh, how big a screen, right? And then it was TCH sketch, right? And there was a little dot on the screen, right? And you were able to spin this arm, and you were able, sorry, not arm, wheel, and you were able to spin this wheel back and forth, right? This one took care of the horizontal. That's saying that if you spun this one, if you spun this wheel right here, right, then your little dot only went side to side. Correct? Right? And if you spun this wheel, right, excuse me, this took care of the vertical. So this wheel did this. It grabbed your dot and moved it up and down. Right? This was the Etch-a-Sketch. Right? So the best idea I can give you, right, is you see the horizontal one, right? This would be your cosine of an angle t. And the vertical would be your sine of an angle t. This right here, I think, is a better explanation of what sine and cosine do. Okay, the cosine sort of describes your horizontal movement left and right, and your sine described your vertical. Okay, now how does that work out? So at the moment, both of these examples that I have here, right, they are based off of a unit circle. So the distance between here and here is 1. But everything here is already set up. That would be my x, that would be my y, that would be my x, that would be my y. So for this one, right, sine of t would be equal to the root 3 divided by 2, and the cosine of t would be the 1/2. 1/2. Right? Over here, same idea. Sine of t would be the y, so it's going to be square root of 2 over 2. And the cosine of t is going to be the negative root 2 over 2. We are done. Okay? Okay. We're getting into good stuff now. So now, let's go ahead and say we wanted to find the cosine of 90 degrees and the sine of 90 degrees, right? Or the cosine of pi and the sine of pi. We have to go back to our unit circle. So in this case, whenever I'm asking something like this, right, we know that 90 degrees, it starts here, right? And it ends, let me make this a little thicker, and it ends up here, right? So just by looking at this, we know what this point is going to be. This point is going to be 0, 1, right? That automatically gives us sine and cosine. So cosine of 90 degrees, excuse me, cosine of 90 degrees is going to be equal to 0, okay? And the sine of 90 degrees is going to be equal to 1. We are done. That is it. We're looking for the x and the y. Okay? All right. Next one. Same thing, right? We're relating this back to our unit circle. We know that the degree angle, that the angle pi, right, it starts here and goes out this way. This is the angle pi, right? So then the point that we're looking at is this point over here, okay? And that point over there is -1, 0. So just as easy as example A, right? Sine of pi is going to be equal to 0, and the cosine of pi has to be equal to 1, -1, -1. Okay? Okay. So now we get to our very first identity. Something that is an identity is something that will always be true no matter what you use it on. Okay? And that is this right here. It's called the Pythagorean identity. Okay? So cosine squared of any angle t plus sine squared of any angle t is always going to be equal to 1. Okay? So there's two things I need to point out here. First of all, why is this true? And second of all, the notation abuse that's happening here. We've already seen some notation abuse happen when we were talking about inverses. Okay, this is another one. Okay, so first of all, let me cover why this is true. Okay, so if we go back to our unit circle, okay, and I'm going to do it like this. I'm going to draw it way over here. Here's our unit circle. Okay. So we know that this radius from here all the way out to here, right? This radius right here, that r, right? We know that is equal to 1. Okay? So remember how I put this down, right? There was going to be a triangle that showed up. Let me actually make that blue a little thicker. There's a triangle that showed up, right? And that triangle had a right angle right here, right? And we know that this side down here, for some angle t, right? So this angle right here is an angle t, right? We know two things. That horizontal length, the side-to-side length, that is going to be cosine of t, right? And this vertical length is going to be a sine. Let me actually do this. Sine of t, right? Okay? If we use these three lengths, 1, 2, 3, inside Pythagorean theorem, it sort of falls in our plate, right? Sort of falls in our lap. So then this says, right, using Pythagorean Pythagorean theorem, right? We have this, right? Cosine of my angle t squared plus sine of my angle t quantity squared has to be equal to 1 squared, which is 1. Okay, and that is basically it. That gave us this thing. Boom. Yeah? All right. This actually brings about my notation abuse. Okay? Notice what I wrote. Okay? Notice what I wrote. And notice where I'm using my parentheses, right? So in this one, I'm grabbing cosine of t. I'm grabbing that entire thing and then squaring it, right? In here, I'm doing the exact same thing, but with sine. So I'm grabbing sine of t, the entire thing, and squaring it, okay? When we write cosine squared of t, right, that is equivalent of saying cosine of t and parentheses outside squared. That is not the same at all, right? Of cosine of t squared. Both of these things, these two things right here, those two things right there, are not the same, okay? So start getting comfortable with this particular notation right here. Okay? That whenever you see cosine squared, okay, or for that matter, cosine of any power. So if you see this, I'm going to write it over here actually. Sine to the fifth of t, right? That is equivalent to sine of t to the fifth. Okay? That is the appropriate notation. Okay? All right. But that's not what we're here for. At least we have to keep that in the back of our minds, though. Okay? We need to get comfortable now with sine, cosine, and in this case, tangent. Okay? So, a lot of this is just repeated use of Pythagorean theorem. So suppose, right, that I have cosine of t equal this, right? And t is in the fourth quadrant of my unit circle. Okay? I need to find sine of t. So, how do we do that? Okay? The start for a lot of these is exactly the same. The difference is how you actually compute sine of t at the end, or the measurement that's missing. Okay? So, step one, I'm going to make my fourth quadrant. Here's my fourth quadrant. So this is quadrant 4, right? Okay, we know a couple things. Cosine of my angle t, right, is going to be 24 over 25, and cosine is adjacent over hypotenuse. Okay? So, and that means we have this going on. Let me go ahead and do my, okay? Okay. And what I'm going to do is I'm going to call this my angle T. So I'm going to draw out the triangle really quick. There we go. This is my angle T. Okay? So then that means my adjacent side is going to be 24. And you know what? I'm just going to bring this down a little bit. Don't need all the space up above it. There we go. I'm going to call this 24. And this is divided by my hypotenuse, which is 25. So this is now 25. Okay? I'm going to actually move this over here just so we can have it out of the way. Because what I'm going to do now is I'm going to solve this using two different methods. Okay? So method 1, right? I'm going to use SOHCAHTOA. Okay? If I use SOHCAHTOA, right, I know that from here, cosine is adjacent over hypotenuse. We have that in our triangle now, right? We need this side. Got it? We need that side, that missing side of our triangle. So we can go ahead and hit it with Pythagorean theorem. Okay? So then we're saying 24, look at me go, 24 squared plus b squared is equal to 25 squared. Okay? B squared squared is equal to 25 squared minus 24 squared. 625 minus 576 b squared. Oh my god. Oh my goodness. Squared is going to be 49. B is equal to 7. Okay? So we found this. Our missing side is 7. Okay? And that's it. Sine, right, of my angle T is opposite over hypotenuse. So then final answer, let me make this a little smaller, huh? Opposite over hypotenuse. It's going to be equal to the opposite of my angle, 7, over 25. Bam, we are done. Okay? This is one method of doing it. So let me go ahead and do a nice division here. Okay? The other way of doing it, right, is using the Pythagorean identity. And that is this thing that's above. The sine squared plus cosine squared is equal to 1. This way, it's one big huge computation, right? Using the Pythagorean identity, but you're going to be messing with fractions. Okay, so let me show you what I mean. So I'm going to start off with cosine squared of t plus sine squared of t is equal to 1. We know what cosine is, right? So that we can just put in here and square it. So 24 over 25 squared plus sine squared of t is equal to 1. We now just need sine of t by itself. So sine squared t is equal to 1 minus 24 over 25 squared. I'm going to carry that up here. Okay. If you do the math right, squared t. This is going to be equal to 1 minus 576 over 625. And if you reduce this properly, 49 over 625. Okay, let me write this really quick. Sine squared of t is equal to 49 over 625. The way that we get rid of a square is that we square root, right? So square root. Okay, if you do the square root of a fraction, the square root goes to the top and the bottom. So sine of t is equal to 7 over 25. We are done. And notice that we get the same answer in both. The answer is the same in both. Okay. I would suggest, right, using one of these two processes. Once you choose one, that's the one you stick with. Okay. So you don't have to confuse yourself. So you don't confuse yourself later, right, when you're doing these on your own. Okay. And I would say this one's the way to go. Okay. It's easy. It's two steps, right? It's 2 steps, but they're easy steps. Got it? Okay. So, quick checks. I'm going to show you guys, I'm going to get you guys to do some of these for practice, right? But now, oh boy. Here we go. We now know how sine and cosine work, where they come from, okay? So the cosine is sort of the fraction between the radius of the circle, right? And the radius of the circle and its horizontal distance, right? And the sine is going to be the radius of a circle divided by its vertical distance, right? Okay. What we're going to do now is we're going to get some common values that we're going to be using on a regular basis when we do trigonometric functions, when we do work with trigonometry, okay? There were a bunch of important angles, right, that we sort of saw when we did 5.1, right? Those important angles were these, right? There was the 30 degrees, there was the 45 degrees, and then there was one more. It was the 90 degree, okay? What we're going to do, right, is we are going to construct sine and cosine. Excuse me. We're going to construct sine and cosine for these three angles, okay? And I want to put these down too. 30 degrees was pi over 6, 45 was pi over 4, and 90 was pi over 2. So we're going to equivalently find the sine, cosine for these radian measures as well, okay? Before we do, I've got to define two more things from geometry. And those two things are these: an isosceles triangle and an equilateral triangle, okay? An isosceles triangle, right, is two opposite legs and two opposite angles are exactly equal, okay? So what I mean to say is this, right? Here's one triangle. It didn't do the ink to shape. Let me do it again. That's horrible. Let me do this. Line, no, and line here, line there. Come on. It didn't want to do it. Oh my God. Let's see. Let's go to shapes. Just grab a triangle. There we go. Woo. Why doesn't it want to grab it now? Come on. Do it again. Okay, there we go. Okay. Isosceles triangle, right? We're saying that this. Oh, good Lord. Now you want to move? Okay. So an isosceles triangle is this. You got to be kidding me. There we go. This angle and this angle are exactly the same, which makes these two sides, this one and this one, exactly the same. So this is what we call an isosceles triangle. Okay? Equilateral triangle. So I'm going to do it again. I'm going to grab, whoa. Oh, come on. Let's see. There we go. There we go. Okay. An equilateral triangle is when all three sides are exactly equal, which means all three angles are exactly equal. So, for example, right, this side, and this side would all be equal, which means all three of these angles, 1, 2, 3, all three of these angles would be exactly equal. These would be the same measurement. And it just so happens that all three of these measurements would be 60 degrees. Okay? All right, so now that we know this, what we're going to do now, this is going to be heavy. Okay? We're going to use these three facts to construct these three measurements right here. 1, 2, 3. Okay? This is going to be the basis, like I said, for a lot of our trigonometric work from here on out. Okay? So the first one that I want to cover is this one. The one for 45 degrees. Okay? So watch this. So for 45 degrees, right, we're going to have this kind of triangle. And I'm going to highlight it out so you guys can see what triangle I'm referring to, this one. There's some kids playing outside. Hopefully you guys don't think I'm like murdering somebody or whatever. I swear, I swear. Okay, so we're looking at that triangle right there. Okay, all right, so I'm going to go ahead and separate that triangle away best I can. I'm going to do bam, right? And you guys can see that this is a 90-degree angle right there, right? All right. We are going back to this radius, the radius of this circle being r equal 1, okay? Okay. So and that means this length is 1, okay? Okay. Since this is 90 degrees, and we know that this angle is 45 degrees, right? This angle right here has to also be 45 degrees, okay? This produces an isosceles triangle. So that means this side and this side must be equal, okay? So if I call this side A, then I have to call this side A. We'll hit it with Pythagorean theorem. So then this means a squared plus a squared is equal to 1. 2a squared, so this is going to be 2a squared is equal to 1. Divide by 2, divide by 2. A squared is equal to 1/2. To get rid of a square, we do a square root, right? So we have this. A is equal to the square root of 1/2, right? Or the square root of 2 over 2. I will show you guys how to do this in class. Okay? So then that means that both of these lengths, this is equal to the square root of 2 over 2, and this is also equal to the square root of 2 over 2. Okay? Grab this triangle, right, and place it right back where you found it, right? And hopefully you guys see why we get this. So then I'm going to go ahead and highlight these. This is this, and this is this. Done. We have found the angle, we have found the measurement for sine and cosine for 45 degrees. Because that's what we were basing all of this off of, right? Bam. Easy peasy, right? All right. So now, I did the 45. Now I'm going to do the one for 60 degrees, okay? Let me go ahead and write that down. So, 30 degrees, okay? Okay, so for that one, I don't want to, let me actually go back up here really quick. We're done with the one for 45, right? We're going to do 30 degrees, so this one. Okay, you guys see your triangle? You guys see the triangle? You guys see it? You guys see it? Okay, so here we go. For 30 degrees, I'm going to use an equilateral triangle. So one of these. Oh boy. Try it again, huh? All right, that's actually pretty good. Looks like a Dorito. Okay. For an equilateral triangle, we know that this, and this are all equal, right? We are going to go ahead and make this equal to 1. All three sides are going to be equal to 1, okay? And since it's an equilateral triangle, we know that the angles of all three angles should add up to 180. That means all three of these angles have to be equal, so each one of these is 60 degrees. Okay? No mystery yet, right? All right. I am going to grab my Dorito, right? And I'm going to slice it straight down the middle like this. Okay, and I'm going to grab one end of it, one side. I'm going to grab this side. Uh-oh, didn't want to erase it all, but I'm going to grab this side. Okay, so we have this. We have this kind of triangle going on now, right? Okay, this is a right angle. We know that this is 60 degrees, right? Which means, and since we sliced it down the middle, right, this should be 30 degrees, right? Got it? Okay. I'm going to give this triangle the boot. I'm going to kick it over this way. So now we have this going on. And this is the triangle that we're going to concentrate on now. Right angle still there, right? This is 60 degrees, right? Just to keep our orientation. And this is going to be 30 degrees. Okay? Got it? Okay. One more thing I want to fill in is this, is that this length right here is 1, which means this length right here is 1, since we just kicked it over, right? Okay. Here we go. Okay. We know that that length is 1. Okay. If you guys take a look, right, this length right here, I'm going to go ahead and highlight it in orange. This length right here. We sliced the Dorito in half, right? So if the original length is 1 and we sliced it in half, that length should be this length, right? Which should be this length, should be 1/2. Which leaves us with one piece missing. This piece right here. I'm going to call it B. So how big is B? This is the thing that we want to find. How big is that, right? This is where we're going to use a Pythagorean theorem, okay? So from here we have 1/2 quantity squared plus B squared is equal to 1 squared, okay? 1/2 squared, that's 1/4. 1/4 plus B squared is equal to 1 minus 1/4 minus 1/4. B squared is 1 minus 1/4, which is 3/4. I'm going to go up here, right? So B squared is equal to 3/4. To get rid of a square, we square root. B is equal to the square root of 3/4. And if you remember your exponent rules, the square root goes to the top and the bottom. So it's going to be the square root of 3/2. We are done. So this missing length B is going to be equal to, and I'm going to erase the red question marks, I'm going to put it in, is equal to square root of 3/2. I'm going to highlight it in yellow. Okay? All right. But we have it. That's it. This right here, this triangle right here, is the one that is going to help us construct the very last bit of our unit circle from above. Okay, so if you take a look, right, let me scroll up. That is exactly that same triangle, right? So that gives us this. This horizontal distance right here is going to have to be the root 3/2, the B that we found, right? And then this vertical distance is going to be our 1/2. Got it? As in my root 3/2 is going to be this right here, my x for that one. And then my 1/2 is this 1/2 from our triangle from below. There it is. Okay, now one more thing. There is this right here. You're probably thinking to yourself, How do we get that one, right? If you take a look at these two, they're the exact same triangle, right? In this case, right, I kicked it over to its long leg, right? Does that make sense? I can go ahead and just grab this triangle right here and just rotate it, right? And I get this. I'm going to go ahead and do it over here really quick for 60 degrees, right? We have this going on now. Right angle there. This is 60 degrees. This is 30 degrees, right? But it's the same measurements as this triangle right here. Everything's the same, right? So then that means this side is going to be a root 3 over 2. This side's going to be a 1/2, and this side's going to be a 1. This right here is how we finish up the triangle for the root for the 60 degrees, right? That's how we get the measurements for this triangle right here. Like I said, all of this is based off of just Pythagorean theorem. You have no idea how much of trig, whoa, what happened there? There we go. You have no idea how much of trig is based off of Pythagorean theorem. Okay? There we are. We have constructed the values for our unit circle. Okay? Okay. To summarize, here's a quick table, right? Not entirely there, but we're getting here, right? I gave you at least the very top portion, the measurements for the first quadrant of our unit circle. Okay. I'm going to make you guys construct the rest as part of your lecture questions. Got it? Okay. So now, identifying the domain and the range of sine and cosine. So we know that sine is the vertical, the y value, and the cosine is the horizontal, the x value, right? This automatically, if you take a look at a unit circle, right? If you take a look at the unit circle, already gives us our domain and range, okay? So remember how these worked, how sine and cosine worked, right? The sine was the vertical, the cosine was the horizontal, right? If you notice for both, right, when we say, let me actually start with the other one. Let me start with cosine. When we talk about cosine, we're talking about the horizontal distance, right? And if you take a look, our horizontal distance goes between here and here. That is it. That is as far as it goes, right? And then when we talk about sine, that is the vertical distance. Bam. This is as far as it needs to go, right? So the domain for both of these are going to be, oh, sorry, the range for both of these are going to be from -1 to 1. That's as far as either one of those functions go, right? And when we were talking about the t values for both of these, so when we were plugging in t values here and here, right, we were talking about the angle, how far, how many times around we went, right? Does that make sense? So this angle, that t, could be any angle we wanted, right? There is no restriction to how big or how small we can put in an angle for sine and cosine, right? So the domain, -infinity to infinity. There's no restriction there. Okay? Okay. So now, reference angles. Coterminal angles and reference angles, people hate them, right? Uh, the reason why we have reference angles, we have coterminal angles, is so that we don't have to use reference angles in coterminal. I know, it sounds super weird, okay? Let me explain what I mean, okay? So to find a reference angle for a particular angle, right, we find the corresponding angle T, right, that lands in Q1. Okay, and the way that we're going to define it is this. we're going to find the equivalent angle that is coterminal that falls inside of quadrant 1. Okay? Okay? So what do I mean by that? Okay? I'm going to give you guys some examples here. So hopefully it doesn't boggle your mind too much. Reference angles of 225 degrees. That's way too big. There we go. Here's our unit circle, okay, or unit oval. 225 degrees. We know it starts here on this ray, and it goes all the way around to right here. Okay, this angle measurement from here all the way around, that is 225 degrees, right? We need the reference angle. So basically saying we want the biggest angle that also lives within quadrant 1 that we can reference when we do our computations, right? Okay. That is equivalent to this angle right here. Okay. And that angle right there is 45 degrees. Okay. So then this means that instead of doing my work and putting 225 degrees everywhere, I can just go ahead and get the numbers for 45 degrees, modify whatever I need, and I have my answers. Okay? I'm going to make you guys do some examples of this in a second. Okay? Let me do this other one. Here's our unit circle, right? 5 pi over 3, that is right here. So start here, and it lives all the way up to, I believe it's like that, way out there. This right here is the measurement 5 pi over 3. Okay? Our reference angle, this angle right here, is pi over 3. And I should highlight both of these. So instead of doing work for 5 pi over 3, I can just go ahead and use the values for pi over 3, right? Modify the stuff that I need, and I'm good. Same way that I was doing it over here. If I wanted to do the work for 225 degrees, right, instead of doing work for 225 degrees, I can go ahead and use the values for 45 degrees. And I'm done. Modify what I need. Okay? This is going to take a little while. Okay? So what I want to do is I'm going to go ahead and have you guys practice a little bit more on the quick checks once we get there. Okay? And then I'm going to have you guys find the sine and the cosine and the tangent of all of them in class, so you guys can all get comfortable using sort of reference angles to find sine and cosines of whatever else you might need. Okay? Okay. Besides that, I think what comes up later is lecture questions. And this is where I'm going to have you do, like I said, let me zoom out a little bit. I'm going to make you guys construct your unit circle. Okay? You know all the pieces. I gave you all the pieces up above. Okay? This, even though you can search it up through Google, try to do it without looking at a reference. Don't try to do it, right, without looking for it on the internet. Pretend you don't know of the internet. Okay? All right. Besides that, that is it. If you have any questions, including this one right here, because this is going to be important, if you have any questions on anything that I just covered, right, ask me during our quick check times or come to my office hours in the tutoring center. All right. Besides that, happy studying.